So, today we will demonstrate experiments on prism using spectrometer. Okay. So far we have shown you the spectrometer, how it works, what are the components of the spectrometer. So, for doing experiment either using prism or grating, so we need to adjust the spectrometer for basically parallel rays and to see the image, right. So, all sorts of adjustment leveling that we have shown. Now, today the spectrometer I will assume that the spectrometer is labeled and it is focused for parallel rays. Now, today we will do experiment using prism. Okay. So, what are the aim for this experiments using the prism? So, aim of the experiments basically determine the angle of the given prism. So, a prism is given. Now, what is the angle of the prism? What is the angle of the prism? So, that one can determine. Then second, determine the angle of minimum deviation of the given prism for a given spectral lines, means for a particular wavelength of light, one can one can determine the minimum deviation of the prism. Third is one can find out the refractive index of the material of this prism. Okay. So, next, this basically minimum deviation depends on the wavelength, angle of the prism does not depend on the wavelength. So, refractive index, if you see the formula, so that also is a function of wavelength. Okay. So, how refractive index depends on the wavelength? So, there is a formula relation. So, that is called Cauchy relation, okay, Cauchy formula. So, that is n refractive index as a function of lambda equal to a plus b by lambda square. A and b are the constant for the prism. Okay. So, refractive index depends on the lambda. So, this is the relation. So, using experiment, one can find out this Cauchy constant. So, that also we will demonstrate, we will perform the experiment. Next, calculate the dispersive power of the given prism. Prism has dispersive power, that is because of this refractive index depends on the wavelength. Okay. So, dispersive power of the prism one can calculate, one can find out. Also, one can find out the resolving power of the given prism. So, if a prism is given to me, then using the spectrometer I can do experiment and I can find out what is the angle of the prism, what is the minimum deviation of the prism for a particular wavelength of a light. Also, one can find out the minimum deviation of the prism for different wavelength. One can find out the refractive index of the material of the prism, and refractive index is a function of the wavelength of the light. Okay. So, one can find out the refractive index as a function of wavelength. How refractive index varies with wavelength, one can find out. Okay. And one can verify the relation between the refractive index and the wavelength that is Cauchy relation, Cauchy formula, okay, and dispersive power, of the prism as well as resolving power of the prism. What are those? What are the meaning of those terms? That let me explain first. Okay. So this experiment is based on purely reflection and refraction of light. Okay. So reflection and refraction, laws of reflection, laws of refraction is well known to all of us, right? But just I repeat those laws. So this is the reflection, okay, from a medium, okay. It can be prism also. So here all of us we know that angle of incidence is equal to angle of reflection, okay. This is the first law. Second law is ignored, but it is very important. Like incident ray, normal and reflected ray remain on a same plane. So this is very important because this is the angle of incidence. Angle of reflection. So this one it can be on this plane, this can be on other plane also, this ray can be on other plane also, okay. So it may form a cone, with the same angle of reflection, okay. So you will see this reflection either in this direction or in this direction with the same angle. So this first law cannot tell. According to first law, one can see this reflection in this direction, also one can see in this direction, okay. But second law tells no, it is not possible to see in this direction, it will be along this direction, because this incidence ray, reflected ray and the normal these three has to be on the same plane. So this is the plane of incidence, is called plane of incidence, is the in this case plane of paper is the plane of incidence, okay. So this second law is very important, although it is ignored, okay. So next, refraction. Refraction, you know this Snell's law. So it's a incident ray and this is a refracted ray, okay. So this is the normal. Again, second law of refraction is same as the second law of reflection. So incidence ray, normal and refracted ray again remains on the same plane of paper, okay. So it can be refracted in this direction, it can be refracted in this direction, keeping the angle same, but this direction is not allowed as per the second law, but as per the first law it's allowed, okay. So and first law is basically Snell's law. Snell's law, this n1 n2 if the refractive index of first medium and second medium, and this incidence angle theta 1 and refracted angle theta 2. So n1 sin theta 1 equal to n2 sin theta 2. If other mediums are there, then also n3 sin theta 3, etc., etc., one can write. So that is the Snell's law. So according to Snell's law, n1 sin theta 1 equal to n2 sin theta 2. Okay. So theta 1 angle of incidence and theta 2 angle of refraction. Okay. So these two cases, one is reflection and another is refraction. So this basically we will use for prism experiment, for prism theory. So then refractive index is very important for refraction, okay. So this is a property of the medium and defined by n refractive index equal to velocity of light in vacuum divided by velocity of light in the medium. Okay. So, that is the refractive index of the medium. Okay. So, one can write n equal to lambda by lambda n. Lambda n means wavelength of the light in the medium, and this lambda wavelength of light in the vacuum. Okay. So, this relation has come basically c velocity equal to frequency into wavelength. Okay. So, from here using this relation one can get refractive index equal to ratio of the wavelength of in vacuum as well as in the medium. Okay. So, light travels from one medium to another medium. That time this its frequency generally does not remain same, only its wavelength changes. So, that is why we have used this relation. So, according to Snell's law, so refractive index one can write that n1 sin theta 1 equal to n2 sin theta 2. So, sin theta 2 by sin theta 1 refracted angle and incident angle. So, that equal to ratio of the uh, refractive index of medium 1 and medium 2. If medium 1 is air, so then n1 will be 1 and n2 is say n. So, 1 by n equal to sin theta 2 by sin theta 1. So, n equal to sin theta 1 sin of angle of incidence divided by sin of angle of refraction. Okay. So, that is the refractive index. So, these are well known. I think in class 10 we have learned about this. Now, prism, we will use prism for this experiment. So, actually various kinds of prisms are available. Okay. Dispersive prism, reflective prism, polarizing prism, okay. Different kinds of prisms are available. So, dispersive prism, they again different kinds of dispersive prism. So, triangular prism, Pellin-Broca prism, okay. Polarizing prism, nickel prism, Wallstone prism. So, these 4 names I have written here because I have used these 4 types of prism. Okay. So, that is why just I have, there are many types. So, but I mention only these 4 because I have used this and probably I will use those prism for different experiment in optics and show you. So, in this case here we will use the triangular prism and it is basically equilateral triangular prism. So, it is this type of shape of the prism. So, this type of shape of the prism. So, it has basically 2 rectangular face, this and this one, and 3 2 triangular face and 3 rectangular face, right. This is triangular face and this one also, and this 3 rectangular face, this one, then this and then other one. So, out of these 3 rectangular face, one is basically is base, okay. It's the opaque one, it's non-transparent, okay, and 2 faces, 2 rectangular faces are transparent, okay. So, for reflection and refraction, we will use these 2 transparent faces, okay. So, when light fall on the prism, then air to this medium there is a diffraction, and again when it exit from the other face, okay. So, here again refraction. So, from medium to the air, okay. So, there will be there. So, this we tell this a emergent ray, this is a incident ray. Okay. So, this is the incident ray. So, this is the direction of the incident ray is this, and direction of the emergent ray is this. Okay. So, actually after refraction in the prism, we are getting light is deviated from the original direction and it is going in this direction. So, what is the angle of deviation? So, if you extend this, so this is the angle of deviation. So, refracted one is deviated from the original direction. So, this is the angle of deviation. Okay. And this is the angle of incidence, this is the angle of refraction. Okay. So, this is about the prism, and this although very simple and well known to all of us. And what is dispersion? Dispersion is the phenomena which gives the separation of color in prism. Okay. So, say white light means it has all sorts of color. Okay. So, it consists of different many wavelengths. Okay. Means of different colors. So, when it pass through the prism, or any other grating, okay, then if the colors are separated spatially, in space, if you see them separately, that is called basically dispersion. And how much this spacing will be between different colors, among different colors, so that is the power of the prism. Okay. So, that we express in terms of dispersive power of the prism. Okay. So, the relation between n lambda for a particular transparent material is given by Cauchy's equation, as I mentioned. So, this is related with this basically refractive index of the material of the prism and the wavelength of the light. Okay. So, this basically it's related with the dispersion basically. Okay. And of course, the larger the value of B, what is the relation here? So, this is the constant A plus B by lambda square. If B is larger, then this dispersion of the medium will be more. Okay. So, that is the importance of this constant of the material. Okay. So, that is why from experiment we try to find out the Cauchy's constant, because if you find the material which is having the higher B value, then the dispersive power of that medium will be higher. Okay. So, now another important characteristics of prism is basically the angle of minimum deviation. Okay. So, prism are characterized by their angle of minimum deviation. So, the minimum deviation angle is achieved by adjusting the incident angle to one of the prism face such that the ray passing through the prism to be parallel to the base of the prism. Means this angle of incidence will be adjusted such that the refracted ray inside the prism will be parallel to the base of the prism. Okay. Then in that condition, under that condition, we will get the whatever deviation, that is the minimum deviation. And in case of minimum deviation, one can also see that angle of this incidence and angle of emergence will be same. Okay. So here I have shown basically this angle of refraction here beta. Okay, that is basically half of the prism angle a by 2, and uh, an uh, angle of incidence is equal to the basically half of the angle of prism plus half of the angle of minimum deviation. Okay. So, from simple geometry one can shows this relation. Okay. And this according to Snell's law, and from there basically n refractive index n equal to sine a plus delta m by 2 divided by sine a by 2. Okay. So, importance of angle of deviation and importance of angle of the prism one can see from here, that if you know them, okay, then you can find out, you can calculate the refractive index of the material of the prism. Okay. So, then next, resolving power of a prism. What is the resolving power of a prism? So, resolving power basically signifies the ability of the instrument, in this case our prism, to form separate spectral lines or images of two neighboring wavelengths lambda and lambda plus del lambda in the wavelength region lambda. Okay. So, what does it mean? That if you have two very close wavelength lambda and lambda plus del lambda, if it pass through the prism, so according to dispersive power of the prism, so these two ray we can see separately after refraction through the prism. Okay. So, whether spatially we can see them, we can separate them or not. Okay. So, that we define in terms of resolving power of the instrument, resolving power of the prism. Okay. And that is basically defined, resolving power of the prism or is defined equal to lambda divided by separation or difference of the wavelength del lambda. So, that is the definition of the resolving power, and for in case of the general definition, it can be for prism, it can be for grating, etc. But for prism one can show that resolving power of the prism is equal to B. B is the length of the base into dn by d lambda. Okay. So, n is the refractive index. So, change of the refractive index with the wavelength. Okay. So, this is the resolving power of the prism. Okay. So, using this formula, so that has come from using the general definition. Okay. So, one has to derive, and it is not very difficult to derive. So, this is the dispersive resolving power of the prism. Okay. So, I defined, I just revise the all terms whatever I will use for the experiment on the prism. Okay. So, next let us do experiment one by one. I think I will just demonstrate first experiment just in next class. So, let me stop here. Thank you.